So this slide shows, on the left, you can see an example of SMOS innovation, observation minus model. For one data assimilation window, we have 12-hour data assimilation window for atmosphere and for land. It's a consistent data assimilation window, which is not the case for the ocean in the weakly coupled system. And what is interesting is to look at, on the top, the table shows the computing time at a resolution of TCO 1279, which is roughly 9 kilometers for a given number of processors and threads. And in the current version, when we compute the Jacobians in finite differences, we have a large computing cost. And in the operational system, it is always getting in the way, it is in the critical path, and we wanted to reduce it. And when we use EDA to compute the Jacobians, we reduce the computing cost by a factor of more than 3.5. And it's the case at 9 kilometer resolution, but also at coarser resolution. So it's a huge improvement in terms of efficiency of the coupled non-atmosphere data assimilation system to use EDA to compute the Jacobians. And at the bottom, we can see the impact for 10 days forecast, from 0 to 10 here, of using the EDA and the SMOS observations on the forecast error. So it's a root mean square error, normalized root mean square error difference between the control, which is the current operational system, and the improved coupled non-surface analysis. And using the SMOS product, so this is on the right for the northern hemisphere, middle for the tropics, and left for southern hemisphere. It's neutral in the tropics and southern hemisphere. In the northern hemisphere, we have a slight but non-significant improvement when we use the SMOS observations. And when we use the EDA to compute the Jacobians, so with enhanced weak coupling, we have a slight and slightly significant improvement, reduction of the errors in the 2-meter temperature forecast. But you know, it's less than 1%. But it's still interesting that it is significant. So it shows the slight benefit of using the EDA to compute the Jacobians, not only in terms of efficiency, but also in terms of forecast scales for near-surface parameters. And this shows maps of the SMOS impact compared to the control, and using EDA, both EDA and SMOS compared to the control. When it's blue, it's a root mean square error reduction, so it's an improvement. When we use SMOS, it's neutral, so we don't expect a huge signal, and it's very noisy, as you can see. Maybe the slight improvement, the slight non-significant we can see in SMOS is due to this blue patch in Africa, but it's a very small improvement. So it's difficult in our systems to improve soil moisture and 2-meter temperature consistently, because soil moisture is already very well constrained by the entire atmospheric data assimilation system, which improves the atmospheric forcing to the land surface. So getting even this slight improvement on the 2-meter temperature from SMOS data assimilation is, we are very happy about that. And on the right, it is a root mean square difference between the new system that will become operational later this year using SMOS and EDA Jacobians, and the current system, which is the control. And with the EDA Jacobians, we know we have globally a small, slightly significant improvement. And we can see the blue patches here in Asia and Australia, also in south east of the US. And on this slide, it is we are using the aircraft humidity and aircraft temperature observations, which are independent, to evaluate the impact of using SMOS neural network soil moisture and the EDA Jacobians. This is a fit to the observation in terms of first guess departure. When we use SMOS here, we can see that the fit to the observation is improved slightly significantly in the low-level atmosphere, in the troposphere. And using the EDA on the top of SMOS doesn't bring additional improvement. So it's interesting because when we look at the aircraft temperature, using SMOS doesn't bring much improvement, but using the EDA to compute the Jacobians does improve slightly and significantly. So overall, having a slightly stronger coupling between land surface and atmosphere, and using SMOS neural network slightly improves the atmospheric scores near the surface. And this is an evaluation of the soil moisture itself, because we want to improve the atmospheric system. We do numerical weather prediction, so priority is to improve the atmosphere, but also another priority objective is to improve consistently the atmosphere and the land surface itself. And this shows that compared to in situ soil moisture stations in the US and in Europe, we looked at correlation, anomaly correlation, unbiased root mean square difference, and bias for the 3 experiments. And the blue highlights the best score for each column. And it's always the SMOS and the SMOS plus EDA, which is performing the best. It's not really significant, but it's consistent that we perform better when we're using the EDA Jacobians and SMOS. So another point, I will go very quickly on this one because I still need to talk about the ocean part. We are using the EDA to compute the Jacobians, 50-member EDA, because in the next upgrade, the EDA, as Elias mentioned, will be based on 50 members. And we tested the computation of the Jacobians with 25 members and 10 members. And here we made a sensitivity test where we double the observation error in the land surface analysis so that we have a degradation, an increase of the error in the forecast error when we double the observation error in the 50-member, 25-member on the top here. And we have the same degradation. The scale is different, but it is in fact the same degradation when we use a 10-member EDA, which is very interesting because it shows that using the EDA to compute the Jacobians is also suitable and relevant to in the testing environment, and also for the next 3 analysis, ERA 6, that will use 10 members. So now I want to talk about the ocean part. We have an ocean system which is called Ocean 5, which is based on NemoVar, a 3D VAR FGAT with 8 to 12-day assimilation windows in 2 chunks. The first one is 5 days at a quarter-degree resolution. And we assimilate in situ observations, temperature and salinity profiles, sea level anomaly, and the OSTIA level 4 sea ice product. We also do an SST, a nudging to the OSTIA SST. And this Ocean 5 system is forced by the atmospheric conditions, which are coming from the high resolution coupled land atmosphere analysis. And in turn, the Ocean 5 system provides conditions to the high resolution coupled land atmosphere analysis. So we now have a 2-way coupling, a weakly coupled approach between the ocean system and the atmospheric system. It's a weakly coupled assimilation system through sea ice fields. In the current system, we only pass from the Ocean 5 system to the atmosphere, we only pass the sea ice concentration. And in the next upgrade, we will also provide the SST in the tropics between 20 south and 20 north, plus or minus 5 degrees for the transition. So then we will have really a weakly coupled assimilation between the ocean and the atmosphere. This slide shows the impact of the weakly coupled assimilation implementation on the forecast of temperature, 12-hour, 24-hour, 12-hour, 24-hour, also for temperature at the bottom, and humidity at the top. And we can see blue is a reduction, and ash blue is a significant reduction of the error. That the improvement is localized in 3 regions, which are where we do effectively weakly coupled assimilation, which is in the polar areas where we have weakly coupled sea ice atmosphere assimilation, and in the tropics between 20 north-south, where we have the weakly coupled assimilation through the SST fields. And we don't have much impact in other areas. As you can see, it's white. And it doesn't go very high in the atmosphere. I have to say that the control here is cycle 45R1, which already uses, for the model, coupled ocean atmosphere forecaster. So it's purely the benefit of having the weakly coupled assimilation and having the atmosphere seeing the right ocean conditions when the 40 bar is running. And it is the same for temperature. We can see that as maps now for temperature at the bottom for 12 hours and 5 days on the right, and for humidity on the top for 12 hours and 48 hours. And you can see for humidity the improvement. Sorry, in fact, it's not humidity and temperature. The top is temperature, and the bottom is skin temperature. Sorry about that. So let's focus. Skin temperature is very close to where we do the weak coupling. So we have the weak coupling between 20 south, 20 north. So the skin temperature is closely linked to the SST. And on the top, this is temperature. Don't look at the right caption. So this is temperature, and we see that the improvement is clearly located on the eastern side of the ocean. And this is where we have quite cloudy conditions, and where we expect that using the Ocean 5 SST is useful, because the austere product doesn't have a full visibility of the ocean sea surface temperature. We also have some improvement in the Arabian Sea, where we have also not shown here some other improvement in the wind condition, and related to the monsoon improvement in summertime. So it's 1 year score, but improvement is stronger in summertime in this area. So now, quick word about outer loop coupling or quasi-strongly coupled assimilation developments. So the original idea was provided by Patrick Laloyau in the context of the Sierra 20C century-long reanalyses. It was at coarse resolution with reduced number of observations, but it was an excellent proof of concept of the outer loop coupling approach. And it was more recently implemented and tested with a full observing system and at higher resolution, still showing some interesting potential, some issues as well that we are working on. But the system was now implemented in our integrated forecasting system in the AFS in a flexible and modular way. So how does it work? We have coupled background model, atmosphere, land, sea ice, ocean, wave, and we are running still land and wave separately, and the analysis between the ocean and atmosphere is coupled at the outer loop level. We are running coupled trajectories, but running separately the minimization for the ocean and for the atmosphere and the ice. This slide shows an example of the root mean square error reduction between the quasi-strongly coupled assimilation and the control 45R1. So we have large reduction in the root mean square error. Still some issues over land, and here it's related in the US to diurnal cycle issues in the coupled trajectories, which switch off the convection in the US. So we are working on that at the moment. And what is interesting is that now it is implemented, it's compatible with the operational environment. It can work for different window lengths, 12 hours, 6 hours, and 24 hours. And we tested it for different spatial resolution. And this impact is really the impact of coupled assimilation itself. Again, the control already has the coupled forecast. And this is an example, just an illustration of the benefit of coupled assimilation on the top compared to uncoupled assimilation using the OSTI SST. This is the Irma tropical cyclone in September 2017. And what you can see on the top in the coupled case, I will put it again. This is Rosé, which followed Irma at that time. So I will start again. In the coupled assimilation, when you follow Irma, you can see a cold wake, which is not at all seen in the uncoupled case at the bottom. So this is the sort of benefit that we have from coupled assimilation in our system. So to conclude, the take-home message is really that we are doing a progressive implementation of coupled assimilation. We start with weak coupling implementation, consistent for land and atmosphere, and now we have it in operations, and nearly later this year. And we enhance the coupling for land atmosphere data assimilation. The weak coupling for will be extended over ocean to the SST. And in parallel to this progressive implementation, we are working on outer loop coupling implementation. Yeah, sorry, nearly finished. And so it was done in the Sierra-SAT system, and now it's all the infrastructure related to the outer loop coupling is in place and flexible to run in different configurations. There are some challenges. So you've seen the issues we have in the extratropics over land in the US, for example, when we use the outer loop coupling. So we are addressing these issues. There are some issues also when we want to do operational numerical weather prediction. We have to account for the fact that for the ocean, the observation latency is longer, particularly for the in-situ observation. So we have to deal with that. And currently, we are testing a combined approach where we combine really the weak coupling and the quasi-strongly coupled assimilation in the same assimilation window. And we are working on coupling through the observation operator, particularly for snow surfaces, and planning to develop our own SST analysis. Another point is that having coupled assimilation in operations has strong implication for all the testing, evaluation, and of the configuration. You know, everyone in the research department is working on a different system. We have to evaluate these systems, and we have to rethink the way we are doing the evaluation of our systems prior to operational implementation. So there is a list of next points to address. Maybe I will stop here, but the idea is that we focus currently on this part, but on the longer term, we will also extend the coupled assimilation to atmospheric composition and river, because we are running these two systems separately. Thank you.
Thank you very much.